Alright, this is a video walking you through the main ideas of test 4-4, which is the level 1 version of this test. Test 4-5 is the one that you can do to get a 4.0. This is the test, the highest grade you can get is a 3.0, but it's a lot more straightforward than the level 2 test. So if we check this out, like there are some important connections between this test, which has position and velocity graphs, and this type of work, which has position and velocity graphs. But the idea here is we are given a description of something happening, and we need to make up all three representations, all three diagrams and graphs, without any numbers. The fact that there aren't any numbers might make things seem a little easier. In some ways they are easier, but in some ways they're tougher. So we're going to see how this works when there are no numbers. I like to annotate the description when I read it for any information that could be helpful. So for example, this says at t equals 0 seconds, Musa is holding a handball. At moment A, he throws the handball in the negative direction toward a wall at a fast constant velocity. At moment B, the ball hits the wall and bounces in the opposite direction, slower than before. And at moment C, Mr. May catches the ball, giving Musa a glance. So the giving Musa a glance part, that's probably not going to show up in our graph. We're going to simplify the situation and just keep track of the important stuff. So I would say you can do these in any order you want to. I'm going to walk through them step by step, but you might find that it's easier for you to start with the position graph or the velocity graph or whatever. What we want to do is use information from the problem to think about how the graph is going to look and how the motion maps are going to look. So I'm going to actually start with the position graph and go from there and see how things go. So I know, for example, between t equals 0 and moment A is shown with this dotted line here. It doesn't have a number, but it's a clock reading in time. Between t equals 0 and moment A, Musa is holding this handball and he's holding it still. So this handball is not moving. I could use my notes in CVM 15.5, and if I look at that section, a graph of something that is stopped, a graph of something that's not moving, looks like a nice flat slope, zero slope. So I'm going to use that. I'm going to have this graph start out at a zero slope position graph. And I could even annotate it and say this thing is not moving. At moment A, Musa throws the handball in the negative direction at a fast constant velocity. I can look at this and say, okay, so a fast constant velocity looks steeper than a slow constant velocity. This is an example of someone walking versus running. So if I'm trying to show that this ball is moving at a fast constant velocity in the negative direction, I want to make this line as steep as I possibly can. Now, I'm not going to finish this. Sorry, my bad. This is supposed to look like this. I'm sorry if you couldn't see that. This line is straight. It is a constant velocity, so I could call this a fast constant V. This line is telling us that this ball is moving towards the wall, and then it hits the wall. I'm not going to finish this graph. I'm going to leave this part for you to finish using whatever information you have. And the fact that it's moving in the opposite direction, slower than before, that's important. I'm going to move on to the velocity and the motion map next. So let's look at the velocity graph first. I know that there's a connection between position graphs and velocity graphs. I can tell, for example, when something's stopped, that the velocity is 0, And depending on whether something's moving fast or slow or positive or negative, the velocity graph will have a nice flat line, but it'll be a larger or smaller value depending on whether it's moving fast or slow. So for example here, when this thing is not moving, I need to make sure that that velocity graph says 0. You can't actually see that I'm drawing a line here because it's directly on the line, but that's what a velocity of 0 looks like on a velocity graph. So I could say not moving to annotate this and show that I understand that this thing is not moving here. Now, when the ball moves at a fast constant velocity, we're going to see the velocity jump to a velocity in the negative direction, and I'm going to make it really strong. That is, like the velocity is a large number. There are no numbers here, but I know that this is like a pretty large number if there were, in the negative direction. What I'm saying is this example shows something moving fast compared to this example that shows something moving slow. These are also different directions, but if something was walking in the negative direction, it might look like that. That's not what we're seeing here. I'm just trying to emphasize that seeing the velocity graph jump down here to a large value in the negative direction tells us that this thing is moving fast. So I can call this a fast constant v. Again, I'm not gonna finish this graph. I'm gonna let you think about what it means for the ball to change direction and move slower. We have a guide of what that looks like here in 15.5, but I'm not gonna actually show you exactly what that looks like for this one. Last step, because I'm doing this out of order just because I thought it was easier to start with a position graph. You might want to start with the motion map if you want to. I need to define a positive direction and sketch a motion map. I'm going to just say that to the right is positive. It doesn't really matter. You can choose either one, but that means to the left is negative. And I know that this ball starts out not moving, and I'm going to show that by showing a few dots that stack up on each other. So this thing is not moving, and I could call this t equals 0 seconds. And then at moment A, this thing starts to move in the negative direction. This is the moment when Musa throws the handball in the negative direction. So we can see this thing speed up and then move at a constant speed towards the wall. So these three arrows show a ball moving at a fast, negative, constant speed until moment B, when the ball changes direction. So one thing that people have been trouble with on motion maps is if something changes direction, how do you handle these dots? I like to put the dot on a second level. If I see this thing changing direction, I know that the arrow has to be pointing over here. So I would make the arrow shorter and I would point it in the positive direction because this thing has bounced off the wall slower than before. This, by the way, would be called moment B. This is the moment when the ball actually changes direction. And notice this says circle and label the clock readings, moment A, B, and C. I would circle this as moment A, and I would circle this as moment C. I'm not going to finish this, but what I need you to think about is, what does a motion map look like when it's moving at a constant velocity? In this case, this is a constant positive velocity because it was negative before. It's moving in the opposite direction, slower than before. So these arrows are shorter than they were. But my last question is for you to finish this up. What's the motion map going to look like if this thing is moving at a constant velocity until moment C when Mr. May catches it? So in order to finish this, you need to actually think about what the motion map looks like for that happening. Last thing. These three questions are most closely related to, I would say, CVM 10. And I didn't write that here, but I'll put that on the test. CVM 10 is the thing that shows us how to check multiple representations. We know now that the idea that we have to check that these are consistent with each other is important. These questions are getting at, can you describe the connection between this idea and between the position graph and the change described in the description in moment A. I need you to actually write a sentence explaining that you described this. One starting point for this is we could say in the description, to start the sentence, to get you started, at moment A, the ball moves fast, negative, and the position graph, ... I'm not going to finish this. You need to finish it. You shouldn't just write ... If you write this but don't finish the sentence and I see it, that means I will know that you just were copying down what you see in this video. I need you to go a step further than that and actually finish this sentence to prepare yourself to write your own sentences on the test that's coming up. That'll be the next step. I'm not going to give you starters for this, but I think that you can do them. This is a useful starting point that could be relevant to these other two questions. You might find that having a motion map in CVM 15.5 is useful to you. So you could try with a pencil making a correct motion map that connects to this. Even one that doesn't have any numbers would be useful for seeing how to connect a motion map to this work. If you've been struggling with motion maps and you need some work with them, that might be useful to have in CVM 15.5.